Okay, so tonight we are going to be talking about first inverse functions, and then we'll get into some exponential functions, and then we'll end with logarithmic functions. So, three different types of functions. Yes, they are related. We talk about inverse functions first because exponential functions and logarithmic functions are inverses of one another. So, we're going to learn about inverse functions first, and then we'll get into using that some to do some stuff with the logarithms and exponentials. So, inverse functions. First thing that we want to talk about is a one-to-one function. A one-to-one function is a function that doesn't repeat x values, and it also doesn't. There's our timer for. Doesn't repeat y values. Okay, so if it's one to one, it doesn't repeat x values and it also doesn't repeat y values. So the not repeating x values is the rule for being a function. The not repeating y values is the special part. That's what makes it one to one. Okay. Now a one to one function, it has an inverse that is a function. So one to one functions have inverses. My handwriting is atrocious today. That are functions. So what that means is that one-to-one functions pass the vertical line test. Remember we did that way back. The vertical line test, if you put the vertical line anywhere on the graph and it touches it more than once, it's not a function. So that's what the vertical line test did. And we also, with one-to-one functions, we get the horizontal line test. Which has the same rules. If you put a horizontal line on the graph and it touches it in more than one spot, it fails the horizontal line test. Okay, so let's look at some pictures of graphs that do these things or don't do these things. So I'm just going to draw a little small coordinate plane. It doesn't have to be real big, and I'm going to put a parabola on it. So there's a graph. That graph is a function. But it is not one-to-one because it would pass the vertical line test, but it's failing the horizontal line test. Okay. Can you put your phone away? Or just, I mean, it can't be more important than what we're doing if you're going to be here. All right, so passing the vertical line test, it does that, but it doesn't pass the horizontal line test, so it's not one-to-one. So that would mean that the inverse is not a function. Now, the next graph, I'm going to try to draw something very similar, but I'm only going to draw one side of the parabola. If you have one side of the parabola, then that does pass the horizontal line test and the vertical line test. So that is a one-to-one function. So this is a one-to-one function. Okay. Another example of a one-to-one function could be just a linear equation, some stuff that we've done. You know, we did linear equations back in 100. That linear equation, that graph, passes the horizontal line test and the vertical line test. To be one-to-one, you got to pass both of them. Okay. So let's look at um, some equations and see if we can tell if they're one-to-one. So let's look at that. So let's say is the function 1, 2, 1? Okay. Is it one-to-one? Hang on a second here, guys. I'm trying to be as bright as possible. And it is not. That'll work. It'll work. All right. Is it one-to-one? Yes or no? So here's our first example. F of x is equal to negative 4x plus 12. Well, I'm not sure. I'm going to graph it and see. Because my best test I've got is the vertical and horizontal line test. So does that pass the vertical line test?
Yes.
Yeah. Does it pass the horizontal line test? So if it passes both of those, then it is one-to-one. So this is a yes. And you maybe put over here passes the vertical line test and horizontal line test. So I just abbreviate those VLT and HLT. So that's how we knew that. We looked at the graph. We saw that happening. Okay. Look at example B here. Call this one G of X, just to change the name there. And let's do the square root of 25 minus x squared. So all of that underneath the square root. And we want to test that the same way. I'm going to look at the graph. If it passes the vertical line test and the horizontal line test, it's one-to-one. If it fails either of those, it's not. So I'm going to go to my calculator, go to y equals, get the square root simple. So second x squared, and then 25 minus x squared. I think that passes the vertical line test, but it would fail the horizontal line test. If I laid a horizontal line there at like maybe y equals 3, it hits 2's place. That's not the only place, but it is a place. One place is enough, where if it hits 2 spots, it fails. So that fails the horizontal line test. So this is not one-to-one. And maybe just put there, just for your notes purposes, it failed the horizontal line test. That was why. Okay. We looked at the graph to do that. Okay. So if it's one-to-one, then it has an inverse function. So we're about to start finding inverses and dealing with inverses a little bit. Okay. So inverse functions. So this is a little definition here. What do inverses do? They swap. Pen to work. Swap the domain and range. Domain is what letter? X values. Range would be the Y values. It swaps X and Y. That's going to be an important thing. You're going to hear that a lot here in a little bit when I say swap X and Y. You're going to hear that a lot. But it swaps the domain and range of the function, of the original function. Close a couple of these tabs and see if that helps us. It's slow on the thing. All right. Now, another kind of definition-y thing here is inverse functions compose to equal x in either direction. So what I mean is that if f of x and g of x are inverse functions, then f composed with g of x equals x, and g composed with f of x equals x. Okay. If they are inverses of one another, if you do function composition, so this is why I wanted to do that lab 13 today instead of doing lab 12, because it had that composition in it. Okay. So if you do that composition, it's going to equal x if they're inverses of one another. It won't have anything else with it. That x will be plain. It won't be negative x. It won't be x plus 5. It won't be 2x plus 17. It'll be just plain old x if they're inverses of one another. Okay. All right. So let's use that idea to test if two functions are inverses of one another. So show whether or not f and g are inverses using function composition. This will be example C. Here's our f of x function, 8x plus 5. Here's our g of x function, x minus 5 divided by 8. Okay. So I'm going to show that in both directions. I'm going to show f composed with g of x. That means I'm going to take the g of x function and put it into the f of x function. So I'm taking this thing and going in for x right there. So that's going to equal 8 times that big fraction, x minus 5 over 8, and then it's got the plus 5 outside. Okay. Now, when I multiply that together, this 8 up here and this 8 down here are going to cancel each other out. Because that's really an 8 over 1, right? Remember cross canceling and multiplying fractions? That's 8 over 1. And 8 divided by 8 cancels out, right? There's 1. So 1 times x minus 5 would be x minus 5. Then what happens with the negative 5 and the plus 5 there? They zero out. Yeah, they cancel each other out. And that leaves me with plain x. Okay? That tells me that I'm pretty sure these are going to be inverses of one another. Okay? I'm going to go and I'm going to do the composition in the other direction. I'm going to go g composed with f of x. So in that case, that means I'm taking the f of x function and putting it into the g of x function. So I'm taking this one and putting it in for x right there. So I've got, instead of x, I'm going to have 8x plus 5 minus 5, and then all of that's divided by 8. So I replace the x with 8x plus 5. Now I'm going to try to simplify that. What happens to the positive 5 and the negative 5? They zero out. So that's going to give me 8x divided by 8. What happens to the 8's? They cancel out, make 1 or just plain x. Right there, I got x in both directions. That tells me that f of x and g of x are inverses. F of x and g of x are inverses. Okay, I want to show you one other cool thing about the functions. I'm going to graph both of them. I'm going to graph f of x. It was 8x plus 5. And g of x, I'm going to put the fraction in there. I've got x minus 5. And then on the bottom, I've got an 8. I'm going to hit graph. Here's the cool thing. I'm going to go down here to y3, and I'm going to put, what was it they were equal to when you did the composition? X. I'll graph that. What is happening here is the graphs of inverses reflect across the y equals x line. So sometimes that's a quick check to see if they're inverses of one another. If you can graph it and they reflect, notice where are the blue and the red line intersecting at? Right on the black line. If they're inverses of one another, that's where they're going to run into each other at, is on that black line, that y equals x line. So inverses also, this is another thing that inverses do, is they reflect across the y equals x line. So inverses reflect across, sorry guys, my pen is acting, the y equals x line. That's another thing that inverses do. So when they do composition, they equal x. When they graph, they reflect across the y equals x line. Okay. So let's try another one here. Let's get a little bit more college algebra level equation. So let's go to the f of x equals x cubed minus 1, g of x equals the cubed root of x plus 1. Okay. Now, I'm going to check it real quick with the graph, but then I'm going to do the composition too, just so that we see all of that. So I'm going to go to my calculator. I'm going to graph in y1, I'm going to graph x cubed, x raised to the third, press the right arrow key, and then minus 1. And then for y2, I'm going to do that cubed root. So to get the cubed root with the calculator, the easiest thing to do is hit the math button. And it's option 4 there is the cube root button. Boom. Cube root, and it was x plus 1. X plus 1. And I'm gonna leave that y equals x line there. Does that look like they're reflecting? Yeah, it does. It's a little bit skewed. I don't know, y'all remember, most of the time now you can get the HD programming and stuff, but back when it first started coming out, sometimes you'd have an HD TV, but the channel was only in standard definition. And when you watch that channel, it would stretch it out sideways, kind of, so everybody's head would, instead of being round, it'd be kind of squished a little bit. The screen on your calculator is that way. It kind of spreads it out more than it really is. You can fix that by hitting zoom square, and it'll adjust it so it looks perfect. That really looks perfect like reflection. But we could kind of see that anyway if we were on the regular, normal 10 by 10 window. We can see that reflecting there. So if I get something when I do my composition that's not X, I probably made a mistake there. That's what I'm going to know. So I'm going to do the composition. I'm just going to do it in one direction here just to show it. I'm going to do F composed with G. So I'm taking the G of X function and I'm putting it in for X. Okay. I've got the cube root of x plus 1, and I'm cubing that because that's what that problem had x doing, and then subtracting 1. So anytime you cube a cube root, it just cancels each other out, and that's going to leave us x plus 1 and then minus 1. What happens to the 1s? They cancel. The sound helps. So x, we got y equals x. That is exactly the right thing to do there. So I'm going to get f of x and g of x are inverses. We saw it with the graph. We kind of proved it with the composition. Technically, if you were going to have to prove this, which we don't have to do proofs in here, you would need to show both directions. Know that it works in both directions. If it works in one way, it's going to work the other way too. Okay, so doing one is enough really for us out of that. Let's do one more. Go back to an easier one maybe. Example E, f of x is 1/2 x plus 5, and then g of x is going to be 2x minus 5. Are those inverses of one another? And so the first thing that I'm going to do is I'm going to graph them and check that first, because that's the quick check to see if they're inverses. So I'm going to go to y equals y1. I'm going to do the 1/2 x. You can do 0.5x. That'd be fine because it's a terminating decimal. Plus 5. And then on y2, I'm going to do the 2x minus 5. Now, it does look like the red and the blue one reflect, but do they reflect across y equals x? No. So you can see where they're crossing is not on the black line. So that should tell me, hey, these are probably not inverses of one another. I'm going to do the composition and just prove that they aren't with the composition in one direction. So I'm going to do f composed with g. So I'm taking the g of x, putting it in for x. So that's going to be 1/2 times 2x minus 5 plus 5. So here we got distributed property. I'm going to distribute the 1/2. So that's going to be x. 1/2 times 2 is x. And then 1/2 times -5 be -5 over 2 plus 5. Are those two going to cancel out? No, definitely not. They actually end up making x minus 2.5, which is not plain x. So this does not equal x. So this is not inverses. So the graph, we saw where they didn't meet up on the y equals x line, and then here we see where the composition doesn't equal plain x. It's got something else with it. So that's not inverses of one another. Okay. So checking to whether two different functions are inverses of one another uses composition. We can use the graph to kind of shortcut it a little bit. Okay, so we always can look at that. All right. The next thing in this lesson is actually taking an equation and finding the inverse of that function. Okay, so that's where we're going next, is we're actually going to algebraically find the inverse. Find the inverse. This pen and I are not getting along. All right, so our first function is going to be f of x equals 3x minus 7. That's going to be our first function. F of x equals 3x minus 7. This is example F. That didn't help any. F of x. This is the cheater one. F of x equals 3x minus 7. All right, now, here's the process for finding an inverse. The first thing you want to do is swap x and y. Remember we talked about earlier in the definition stuff that an inverse swaps the domain and range, or swaps x and y. So the first step is you're going to swap x and y. So in this equation, the y is the f of x thing. So I'm just going to call it y. And I'm going to write this as x equals 3y minus 7. So you literally just swap the places with x and y. Okay, so that's step one. Step two is you solve for y. Okay, so we've got that equation. We've got the x equals 3y minus 7. I'm going to get y by itself. So what would be my first step? Add 7. X plus 7 is equal to 3y. Y is almost by itself. We got one more step. Divide by 3. And I'm just going to divide every piece by 3. Like that. What's in front of that x there? A 1. That just helps me get a slope of 1/3. X plus 7 over 3 is equal to y. You have found the inverse. So the last step is rewrite this into inverse notation. Inverse notation is this. It was f of x to begin with, so to write inverse, you write an f, then a little -1 exponent, x. The way that's read is f inverse of x is equal to 1/3 x plus 7 over 3. That's the inverse function notation. If you graph the original, which was 3x minus 7, and then we graph the inverse that we found. We use the fraction for 1/3. Put the x out there beside it, plus, and fraction, 7/3. And are they reflecting across y equals x? Yeah, absolutely. So that we found the right inverse. So if you want to check your algebra there, if you made any kind of mistake, then they won't reflect across y equals x. That's always a good checking thing to do. Okay. All right, let's do one that's a little bit more difficult. I'd say difficult. It's really not that hard, but here's our function. H of x is equal to x minus 3 to the third power. Okay. So we've got a cubic function, and we are going to try to find the inverse of that. Okay. So the cubic function, first thing that I'm going to do, what's step one? Swap x and y. So that's going to be x equals y minus 3 to the third power. Now, if I'm going to get rid of get y back by itself, I got to get it out of that parentheses there. So I got to get rid of that cubed. So what is the opposite of raising something to the third power? Not the square root, but the cubed root. Yeah, same. That's what you meant. I know what you meant. So we're going to take the cubed root of both sides. So the cubed root, you got the little index of a 3 up there on your radical. So we got the cubed root of x. And on the right-hand side, the cubed root and the cubed cancel each other out, and that gets us just y minus 3. So we're one step away from getting y back by itself. What do we do next? Add 3. Yeah, simple addition of 3. So that's going to be the cubed root of x, and then we got the plus 3 on the outside is equal to y. Last thing is just rewrite it in the inverse notation. So h inverse of x equals cube root of x and then a plus 3 on the outside. Three-step process every time to find the inverse. Not always quick and easy on the algebra. It has been on these two. We're going to do some that are, I probably say these are the most challenging of the inverse finding ones. They look innocent, but they're really not. They're not hard, but there's a little trick to them. So let's look at example H. Here's our function. It's a rational function. Remember, we did those back in January, back before Snowmageddon, Ice-mageddon. I don't know which one it was, but we did these rationals way back in January. Okay? So 2x plus 3 over x minus 4. So that is a function. It's a rational function. That really doesn't matter, but we're still going to take the same process for doing this. The only difference is there's two places where there's x. So when I do that first step, I'm going to swap the x's and the y's. That's going to be x equals 2y plus 3 over y minus 4, like that. That's step one where you swap x and y. It's everywhere there's an x, it becomes a y. All right, now here's where the fun begins, okay? So because we got a big fraction over there, we want to make it not a fraction. So the easiest way to do that is to just multiply both sides by that denominator. If I do that, on the right-hand side, it's going to cancel out. On the left-hand side, what property is that? Distributive property. So I'm going to distribute that x to the y and the 4. So that's going to be xy minus 4x. And the right-hand side, all I got left is 2y plus 3. All right, so the purpose is to try and get y by itself, okay? So we want the y's to be by themselves. So I need to get the things that have y on one side, the things that don't have y on the other side. So the things that have y are xy and 2y. So I need those on the same side. And on the other side, I need the 4x and the 3. Okay, so I'm going to move the 4x, and then I'll move the 2y. Okay. So I'm going to move the 4x by addition. That'd be xy equals 2y plus 4x plus 3. Okay. Now I want to get the y's over there together. So I'm going to move this 2y. It's a positive 2y, so to move it over to the other side, what do I need to do? Subtract it. So I'm going to subtract 2y. So I have xy minus 2y equals 4x plus 3. Now, next thing I want to do is, this is the trick to these, okay? This is the most important step. Once you get the y's on the same side, factor a y out of the left side. Okay, so both of those have y. So I'm going to factor y out. So y, then x minus 2. And then the other side is still the 4x plus 3. So I took that y and I pulled it out. And that left me the other stuff, the x minus 2. Now, what's going on between y and that parentheses x minus 2? What operation? What's the opposite of that? Division. So I'm going to divide by the parentheses there to get y back by itself. So I'm going to divide by x minus 2. Now I have gotten y back by itself. So I'm ready to rewrite this in inverse notation, which we started out with f. So f inverse of x equals 4x plus 3 over x minus 2. Not the easiest thing in the world, but it's not too terribly complicated. That factoring step is the thing that gets most folks, is they forget to do that factoring step. You can graph the original and graph this one. They are inverses of one another. They do reflect across y equals x. Let's do another one of those. Let's say g of x is equal to 3x minus 8 over x minus 5. Okay. Now, first step. What do we do? Swap the x's and y's. So instead of g of x, that's going to be x. Instead of 3x, that's going to be 3y. And then instead of x on the bottom, that's just going to be y minus 5. All right, so now we've swapped x and y. Now we got to get rid of that fraction. So the easiest way to do that is to do what? Yeah, multiply by that denominator. That denominator is that y minus 5. It gets rid of it on the right-hand side. Don't need anything to do there. Just cancel it out. So the right-hand side, I got the 3y minus 8. What's on the left? xy minus 5x. Good. Now, move the y's to one side, the things that don't have y to the other. Doesn't really matter which side you go to. Just
Can we do both at the same time?
That's what I'm going to do. I'm going to do both at the same time here. I'm going to move the 3y and the 5x at the same time. So I'm going to move the 3y by subtraction and the 5x by addition. I'm just doing that all at once. Is that what you mean?
Yes.
All right. So the 3y on the right cancels out. The 5x on the left cancels out. So I get xy minus 3y. And then I'm going to write it as 5x minus 8. I just like putting my letter stuff in the front. It really doesn't matter, but I like having the x's in the front. Keep your x's in front of you where you can see them. You don't have to worry about it. Joke, kids. All right. Now what?
Factor out a y.
Yeah, now the tricky step. Factor out the y. X minus 3 left inside. And then divide by that x minus 3. So there's our y by itself, 5x minus 8 over x minus 3. And then we rewrite it. G inverse of x is that mess right there. That's an 8, not a 5. We found the inverse. And again, we can always graph it and check. Okay. See if it reflects across the y equals x line. These rational ones are a little harder to check with the graph just because there's so many pieces sometimes. So it's a little tougher to check them. But it still, you would still be able to recognize it, I believe. You guys see that pattern pretty well. All right, one more in this section, and then we'll move on. Example J. Let's do f of x. Let's do a square root. So the original one is the square root of x plus 5, which is a one-to-one function. Let y'all find the inverse of that. See if you can find the inverse of that. It's very similar to the one with the cubed that we did. It just has the root to start with instead of the exponent to start with. See if you can undo that. Get some money math tonight. That's awesome. I'll kind of slow play behind you here. Hopefully that's your first step. How do you get rid of a square root? Square them. Okay, so I'm going to square both sides. So when I square both sides, that's going to give me x squared is equal to y plus 5. The square root goes away. That's good news. One more step. Get the y by itself. Okay. Subtract the 5. You got x squared minus 5 is y, and it was f of x. So f of x, or f inverse of x, x squared minus 5. Now, here's a little bit of a kicker on this one that doesn't always come up. We know that the x squared graph is a parabola. What you need is 1/2 of that parabola. So technically, it would be for x's that are greater than or equal to 0. That's more of a college math 140 thing. They usually don't even ask about that at all for the math 110. I've never seen that on the final. I don't ask about it on my test or quizzes because I've never seen it on the final. But you still could find the inverse by swapping x and y solving. That's same thing. Okay, so that's section 1. Good news. Section 2. Let's do some exponential stuff. Exponential functions is section 2. 4.2 exponential functions. Exponential functions are functions that look like this. You have a base. I'm going to put a letter A just as the base. And you have x. So that's your exponent. It has the variable in it. This is called your base. And it's usually a number. That exponent can have some other stuff happening in there, like it might have x plus 3 or something weird like that in there. But the variable is in the exponent with a exponential function. That's where the x lives, is in the exponent out of that. All right, so with exponential functions, there's 2 types. You have exponential growth and you have exponential decay. Okay, so exponential growth, I'm going to sketch the graph real quick and then we'll write an equation that's exponential growth. So I'm drawing my coordinate plane, kind of more in the upper, first and second quadrants. Exponential growth does come something like that, where it goes up and to the right really fast. It goes up really fast. Doesn't go to the right really fast, but it goes up really fast. Exponential growth is like a really common example for it is a savings account at the bank. The formula they use to give you interest in that or any interest bearing account is exponential growth. That is a common example for that. Exponential decay goes in the other direction. It goes down and to the right quickly. Unfortunately, my bank account is exponential. No, I'm just kidding. But exponential decay, probably the most common thing there would be decomposition of plants or anything like that. Like the mulch you put out last spring has been decomposing exponentially since you put it out. And, so that's why you need new mulch this spring because what you put out there decomposed. So it decomposes at an exponential rate. Um, Another exponential growth example, since it's flu season, is bacteria and germs. They grow exponentially. That the cells divide. You got one cell, it divides into two. Those two cells divide into four. Those four cells divide into eight. Those eight cells divide into 16, and before long, the whole table is covered in germs. Right? That's what's going on. That's why people are sick. Uh, Unfortunately, exponential decay doesn't work with germs. You got to wipe them all out with Clorox or something like that. But anyway, exponential growth. The keys to that, when you have the function, it looks very similar, but the base is going to be a number bigger than one. Exponential decay, your base is a number between 0 and 1. So it's a small fraction. Okay? Growth, the base is bigger. Decay, think about the base is a decay and decimal maybe goes together. You could write it as a decimal really easily. So we think about small fractions as decimals a lot of times. They will write it as a fraction, but you think, oh, that's just a decimal for, 1/2 is 0.5. That's the decimal. That's decay. Okay. So let's look at some examples of functions and decide, is this growth or decay? Is this exponential growth or decay? State the domain and range. We hadn't done that in a little bit. Example A, f of x equals 4 to the x plus 1. Is that growth or decay? Growth. Because that number is bigger than 1, this is growth. The domain, here's the cool thing, is always negative infinity to positive infinity. Just always is that. Okay. The range, because this one doesn't have a vertical shift, it has a horizontal shift. It doesn't move up or down any. The range is going to be from 0 to infinity because it goes up from 0 to infinity. Okay. So example B, f of x is equal to 1/3 to the x power. Decay, because 1/3 could be written as the decimal 0.3 repeating. So anytime we have a small decimal, something less than $1, that's a decay. Okay, so we have decay here. Even though it's decay, the domain stays the same. It's still from negative infinity to positive infinity. The range, this one doesn't have a vertical shift, so it also is from 0 to infinity, which seems weird, but if you're decaying, the lowest you could ever get would be to 0. You're never going to have negative germs, right? That's not possible. You can either have no germs or a bunch of germs there, but you're never going to have negative germs. That's just not going to happen. Even if you've got what is the saying? The stuff you can buy like, well, it's a like if you buy a new shower or something at Lowe's or something, that a lot of them have this word. Oh, antimicrobial is the word and it means it's supposed to repel germs. It never can get below zero, though, right? It could have no germs on it, or it's got germs on it. It's never going to have negative germs on it, right? Even though it repels them, it still could have some on it. So decay range is always going to have that bottom line at that. Now, I keep saying something about a vertical shift. Let's look at one that has that and see how it affects things. So here's as a g of x equals 2 to the x power, and then not in the exponent, down here with the 2, I'm going to put a plus 3. Okay. So first thing I want to know is this growth or decay? Why? Yeah, that base on the exponential is a 2, so that is a growth. The domain is still going to be the same, negative infinity to positive infinity, like the most boring domain ever. The range, because it's got this plus 3, that is a shift up, not to the right, but up 3, because it's not with the x. Like number or example A, we had that x plus 1 in that would be a left 1. If it were right, it'd be a minus 1. But if it's not with the x, it's down there kind of hanging out on the end, that's a vertical move. So that's a vertical shift up 3. That changes the range, because instead of being flattened out at 0, it flattens out at 3, whatever that vertical shift is. So our range is going to be from 3 to infinity. And it's because of that. That's the reason out of that. Not that that comes up a ton, but I want you to see it just to say, hey, we talked about it a little bit. It doesn't come up very often, and you can also graph these things with the calculator. That's the great thing about this, is you guys have these graphing calculator tools that we didn't have when I was going through high school, and we didn't really have them when I was going through college algebra. They existed, but nobody could afford them because they were like super expensive back in the 1900s, you know. So they still are, but they're a little less expensive than they used to be. Compared, like $100 now is not the same as $100 was back in the 1900s. It's still $100, but it's not the same $100. So, like if I graphed 4 raised to the x plus 1, I can see that graph on my calculator. You can see it flattening out at 0. But if I do that, well, we had 2 to the x, and then the plus 3 was hanging down here. Look where it flattens out right there at y equals 3. So we can see that with the graph. So we can use the graph to kind of cheat our way through some of the range things. It's not really cheating. It's using a tool that you have to help you with that. So the range, you can really get a little help from the graph out of that. Okay. All right. Now, next part is my favorite part of this section, which is actually solving equations. I love the times when we get to solve equations because we get an answer and we got something. We did something, we accomplished a goal, we got through with something. So let's solve the exponential equation. And I'll put on here, this is level 1 easy. Okay. We'll get to some in this chapter that are not level 1 easy. They're going to be a little bit more difficult. But level 1 easy, these are not hard to do. Okay, so we're going to solve the exponential equations. So the key to solving exponential equations is get the base. Base is a B, not a P. The base the same on each side. If you can get the base the same on each side, then it's level 1 easy. Okay, so example D, we'll start with one that already has the base the same. 5 to the x equals 5 to the third. The base are those 5s there. Since they are already the same, then that must mean that the exponents have to be equal to each other. So we just set up the equation x equals 3. And if x wasn't by itself, I'd have to get it by itself. Here, it's just plain x. So I don't have to do anything. I'm done. That's just x equals 3. That's like almost too simple to really learn anything from. So let's get one where we got to learn something here. So let's go to example E, where we maybe have 5 to the 2x equals 125. Okay. So kind of thinking along the same lines as example D, the left-hand side, we have 5 to a power. On the right-hand side, I want to make that 125 5 to a power. What power is 125 as far as 5 goes? 5 squared would be 25. 5 to the 5th would be much larger than that. 5 to the third, yeah. 5 times 5 times 5 is 125. Okay, so we have the base is the same. We've rewritten that problem with the same base. Now, because the bases are the same, I set up the equation 2x equals 3. Now I got to get x by itself. So what do I do? Yeah, just divide by that 2, and x ends up being 3 over 2. And we solved it for x by getting the bases the same. Let's try another one. Let's say we had 2, I said 2 and wrote 3. 2 to the x plus 1 equals 16. So on the left-hand side, I see a 2 as a base. So that 2 doesn't break down any. 2's prime, right? So that means 16 needs to break down some. So is 16 2 to a power? It's 2 to the 4th. So this is really 2 to the x plus 1 equals 2 to the 4th. Now I've got the bases the same, right? Yeah, set x plus 1 equal to 4. So once I get the bases the same, set the exponents equal to each other. And then it's an easy equation. Subtract 1, x equals 3. See what I mean by level 1 easy? Once you get the bases the same, the equations are not very difficult. Let's try this one. Let's say we had 3 to the 4x equals 243. Just going to stretch you a little bit on some numbers, and it's okay to use the calculator to kind of help you figure out what 243 is. 3 to the who? 5th. 3 to the 5th. So we have 3 to the 4x equals 3 to the 5th. Bases are the same. So our equation that we're going to work is what? Yeah, 4x equals 5. Divide by 4. X is that fraction, 5 over 4, or 1.25 if you did a decimal there. Same thing. Right? So if the base on the left side's prime, then you just got to work with the other side and get the base the same. Let's try one more. Let's say we had 3 to the x plus 1 equals 27 to the x. So this one's got x's on both sides this time, which makes us a little nervous sometimes, but it's still doable. (27) is 3 to the third. So that means that's going to be 3 to the x plus 1 equals 3 to the 3x. That's what that turns into. The reason being is that's 3 to the third to the x power, and the exponent rule is that you multiply those two together. So that's how I ended up here. Now, the bases are the same on each side, so I drop them. I have x plus 1 equals 3x. How do I solve that? Subtract, no, not subtract 1. I can't divide by 3 because I got to get what together first? Subtract the x to get the x's together. I got to get like terms together before I can do any of that stuff. So let's get the like terms together. So that's going to be 1 equals 2x. And then divide by 2. Yeah. And we get that x equals 1/2 here out of that. Not too bad. That's doable. Where it gets more interesting is when we have things where both sides are not prime. Okay, so let's say we had something like, where does that go? I just keep writing it and it disappears. Let's go 4. Did it again. 4 to the x plus 5. Oh, I know why. It's converting it to text. See it down there? Somehow it thought it was that. I hit that pen there, the one with the little letter A in it. It's supposed to try to read my handwriting and write it and make it type it. It doesn't do a very good job. It is nothing like iPad does a lot better job. Maybe I should learn to write better. That could probably help. But all right, so here we got 4 to the x plus 5, and then 8 to the x minus 1. So this one really steps it up because I know 4 is not prime and neither is 8. But I want to think exponentials here, not really thinking about 4 times what is 8, but thinking about how could I rewrite 4 as a something with a base and an exponent, and how could I write 8 with maybe the same base and an exponent. Very good, very good. The 4 is 2 squared. The 8 is 2 cubed. Okay. So we've got the bases the same. What's the rule for those exponents? What do I do with them? Yeah, but what operation's going on between the 2 and the x plus 5? Multiplication. So I'm multiplying 2 times x is 2x, and then 2 times 5 would be 10. And on the other side, what do I have? Yeah, 3x minus 3. Now I've got a fairly simple equation to solve. Whichever way you want to go, get your like terms together. I'm going to go x's to the right, numbers to the left. 13, 3x minus 2x is 1x. No sense in dividing by 1, doesn't change anything. So x is 13 there. Now that might be level 2, 3-ish probably, because you got to do a lot more stuff. But it's still not terrible. Just getting the base the same there. So that's a little higher level than the first ones that we did, but it's still not just crazy hard. All right, let's try this one. I don't know what letter we're on. J. Let's do 9 to the x plus 5 equals 27 to the 2x minus 1.
3 squared and 3 cubed.
Yeah, 3 squared, 3 cubed. So it's a base 3 this time. 3 squared, x plus 5, 3 cubed, 2x minus 1. And then, so what's our equation that we're going to be solving? 2x plus 10 equals 6x minus 3. Solve it whichever way you want to. I'll go the other direction this time just to change it up. So I get a negative 4x equals negative 13. And then divide by the negative 4. What's that become?
13 over 4.
Yeah, positive 13 over 4. Or 3.25 if you did decimals there, but typically we're going to leave that as a fraction. Questions about the easier exponential solving? We'll get into some more difficult ones later on that you can't do this with, but we got to learn some other things before we can do that. Okay, so right now we got all the skills that we need to be able to solve those kind of equations. So the next thing in this same section is some financial math. Okay, so we talked about a savings account or any kind of interest-bearing account. So let's do a little bit of compound interest here. Compound interest. You have a formula. A equals P times 1 plus R over N to the NT. Okay, so let's find out what all of those letters mean. Okay, so A is your account value. P is your principal investment. Think about that as your deposit. How much money you put into that account is that principal investment. The R is your interest rate. Make sure you change that to a decimal. So they're going to give you the interest rate as a percent. Make sure we change it to a decimal. The N is the number of times compounded. In a year. Typically, if you went to one of the local banks here, Home Banking or Bank of McNary or Cadence Bank, or, well, is Cadence Bank, is Huntington Bank now? They may not change their name, though. I think Huntington Bank owns Cadence Bank now because they owned my mortgage, and now Huntington owns my mortgage. But they said Cadence was still going to keep my mortgage. It's weird. Anyway, CBNS, any of the banks in town, if you go get a savings account, they typically give you your interest quarterly, which quarterly means 4 times a year. That's typically how they do interest. So the N would be 4. You can find accounts that give you interest monthly. So N would be 12. There are even accounts that give you interest weekly. They're hard to find, but they happen. And, N would be 52 then. Okay. So N is how many times they're going to give you your interest out of that. Some accounts only give you your interest once a year. At the end of the year, they give you your interest and that's it. Okay. And then and 12 months later, they give it to you again. Okay. So the N is the number of times that your interest is compounded in a year. T, and I'll roll back up to where you can see that formula there. T is that up there in the exponent. That's your time in years. So anytime you're dealing with financial math or anything with the bank, they're talking about everything within a year. They may It kind of gets you a little bit like that. If you look at a certificate of deposit, a CD, they'll have an ad for it in the paper, and it may say that it's a 6-month CD, and it offers a interest rate of like 7.5%. Well, what they don't tell you is that's 7.5% over a year, not 7.5% over 6 months. So in 6 months, you're only getting half of that. So they don't tell you that in the ad, but it's in the fine print. If you look, there'll be a little star by it. You look down at the fine print, it'll say that's AYP, which is annual, or APY, annual percentage yield. That's yearly out of that. So the bank does everything by the year. Okay. So this formula is what we're going to use to find out how much money we'll have. Okay. So let's do a couple of examples of this. We're not going to do anything too crazy with this. We're just going to take some money and put it in an account. See what happens to it. Okay. So I don't know what letter we're on, but we're on example K. Let's say we invest Let's say we sold our first car because we got a new one and we want to take the money from that and put it in the bank and set it aside, hopefully, to just have a nest egg sitting away. So we sold our car for $2,500. We're putting that into an account. Drawing 6% interest over 5 years, compounded quarterly. What is the account worth after the 5 years is up? A little bit of a word problem. That's okay. So here's what we got. We got our formula. If you'll write it down every time I write it down tonight, you'll probably have it memorized and won't have to really study too hard at memorizing it. All right, so I'm going to go back through my word problem and I'm going to write down what letter each thing goes with. Okay, so where does P go? My principal investment. 2,500. That's P. Okay, so that's my 2,500 is P, and then it says drawing 6% interest. 6% is my what? My rate, right? So R equals, what's 6% as a decimal? 0.06. So that's where that 6% is coming from. And then the next number I see is 5 years. What is that? T, yeah, time in years. And then it says compounded quarterly. Where does that fit in? N. What is N? N is equal to 4. Quarterly, there are 4 quarters in a year. So every 3 months is what that means. Okay. So we have everything that's in that formula except for the account worth, and that's what they want me to find. So they want us to find A. So I'm going to take those things and plug them in. So I have 2,500 for my principal. 1 plus 0.06 divided by 4 to the 4 times 5. I'm just going to go straight to my calculator and I'm going to type that in just like that. I got my principal. The 1 is always there. Then I've got my rate as a decimal divided by N. And then the exponent is N times T. So 4 times 5. On my calculator, I'm typing that in. 2,500 parentheses 1 plus. I'm not even going to do the fraction thing. I'm just going to do 0.06 divided by 4. Close the parentheses. Then I'm going to hit my little caret symbol, little house top symbol over there above the division symbol. And then up there, it's going to be 4 times 5. I can actually just type in 4 times 5. If I want to write 20, I could, but I'm just going to type that in. That is exactly what I had written down there. So I'm going to take that and just hit enter. That's going to tell me how much my account has in it after 5 years. $3,367.14. $3,367.14. Anytime we're doing money problems, we want to round to the nearest cent, unless the problem says maybe round to the nearest whole dollar or something like that. If it says something different, then do what it says, but most of the time you're going to round to the nearest cent. Okay. Compound interest. The only things that are going to change are really your N and your T. And then they might have a different interest rate. But as far as that goes, nothing really crazy there. Let's do one more. How much should I invest at 3.5% interest? Compounded monthly to have $15,000 after 10 years. So I want to put some money in an account and leave it alone for 10 years, but I want it to have $15,000 at the end of that 10 years. Okay. So in this problem, what do I have? So I know I got to have my formula. A equals P1 plus R over N to the NT. What things do I have? I have A. What is A? So this is A. Okay. 15,000 over there. Good. What else? Say it again. Time in years. I got time in years. That's T. So that's going to be something times 10. And I have the interest rate. That's R. Monthly. So what that monthly tells me that N is what? 12. So that's going to be 12 times 10 up there. I always have the 1. My interest rate is 3.5%. What is that as a decimal? 0.035. Be careful about that. I know we all know that, but sometimes we get in a hurry, and that's a lot of times the most common mistake is we won't move that decimal twice. We'll just move it once and accidentally work it the wrong way. 12 goes on the bottom. P is the thing I'm missing. I'm missing the principal investment. That's what I want to know. How much money do I need to stash away in this account that's drawing 3.5% interest? Okay, so I'm gonna find that. So this stuff over here, that's just a number. Okay, it's a number times P. So to get what P is, I'm just going to divide by that number. Whatever that number is, I don't know what it is. And I'm not going to round it until I get done. So this is where the calculator really comes in handy. I'm just going to write that as 120. So on the calculator, I'm taking my 15,000 divided by, and I'm gonna open up a couple of sets of parentheses here because I want all of that stuff that I type in there to be in the bottom. So parentheses, and then I've got 1 plus 0.035 divided by 12. Close those parentheses, raised to the 120th power. And then I'm going to close those parentheses. So that gets all of that stuff in the denominator of the fraction there and hit enter. So I'm going to have to stash away $10,000, $10,575.71 to gain what amounts to be $4,500. 10,575 and 71 cents. That's how much I need to put into that account and just let it be. I don't know anybody that's got 5 hanging out that they can just put in the account and let it alone. I don't. Be nice if I did, but I don't. But that's what we got to do there. So got a little bit of finance stuff put in there with the exponential functions. As we get a little further along into this chapter, we will be going back to this and solving some stuff for time and solving for the rate and solving for the end, stuff like that. Mostly solving for time is what we do a lot in here. So, but we got to have some other skills to be able to do that. So that'll come up later in the chapter. Okay, or next week actually. So, all right. So 4-1, 4-2. Next is 4-3. And 4-3 is we're going to get into logarithmic functions. Logarithmic functions, which is the inverse of an exponential. So find my page here. 4.3 logarithmic. I in there. Functions. Okay. And just like I said earlier, logarithms are inverses of exponentials. So with an exponential, we got a to the x equals y. And let's go to the parts again. This is the base. This is the exponent. With a logarithm, this is the base. This is the exponent. Those two equations there, even with those, they've got only letters in them, they are inverses of one another. That you can rewrite an exponential as a logarithm. You can rewrite a logarithm as an exponential. And that's what we're going to do first, is go back and forth between those two different forms. Okay. And it's weird to look outside and it still be bright out there. I'm looking at it, I'm like, golly, it's almost 7 o'clock and the sun's still shining. So I feel like we're flying through this stuff, but we're really not. So, all right. So the first set, we are going to rewrite write the logarithm as an exponential. So write the logarithm as an exponential. Y'all remember doing this in Algebra 2 in high school? Maybe. I don't know how much you did of it. Depends on when you had it. But you've probably seen these before. You may not have as much experience as other people do. It's not real difficult. We're going to learn it now, and you'll be fine. It's just not a hard thing to do. Okay, so we're going to start with a logarithm. So my first example, I have log base 3 of 81 equals 4. So here's the decoding that. This 3 is the base of our exponential. This 4 is the exponent. Three to the fourth power is equal to 81. That is rewritten from logarithmic form into exponential form. Very, very easy thing to do, but being able to rewrite it in that different form is going to help us when we get into solving some more difficult equations sometimes. Okay, so rewriting that. Okay, so the way you read that logarithm really helps you learn to do that. The way you read that is log base 3 of 81 equals 4. If you'll read it like that, then that automatically helps you rewrite the exponential as the base 3 to the fourth power equals 81. So let's do another one. Here we have log base x of y equals a. So we're rewriting that, even though it's all letters, we're rewriting it as an exponential. What is the base of the exponential? X. What is the exponent of the exponential? A. A logarithm is always equal to the exponent. So anytime you got the equal sign in a logarithm, whatever's on the other side of the equals, that's the exponent. And then the only other place for y to go is on the other side of the equal sign. Let's do one with numbers in it. Log base 3 of 1 over 27 equals negative 3. A lot of threes in this one. But what's the base? Positive 3 is the base. What's the exponent? Negative 3. And then that leaves only one place for the 1 over 27. Let's try another one here. Log base 2 of 256 equals 8. What is that in exponential form? Base 2 is important if you like computers or electronics. Base 2 is what all of that's based out of. Do you remember, if you buy your iPhone, if you ever notice, how many gigs can it have? You do 128 gig, 256 gig, 512. They're all base 2s.
Now there's one
Terabyte,
terabyte.
which is terabyte is all right. So a gigabyte or 1 gig hold on, 128 gig, 256 gig, 512, 1024 gigabytes is a terabyte. That's what a terabyte is. So 2 terabytes is 2048. Actually, it's not 2000. It's 2048 gigabytes. It's all base 2. That's what it is. Nerdy things you don't have to know, but it's neat to see happening around you. So numbers are always there. All right, let's get so base 2 is important in electronics and computers and stuff like that. Base 10 is what we live in. Okay, so when you have a logarithm that doesn't have anything written there, that is a base 10 log. This is called a common log. And that's base 10. Base 10 is the number system we live in. And the reason it's the number system we live in is because all the numbers that we use, like if I gave you the number 374, in base 10, the 3 is in the hundreds digit, right? so that's 10 squared. The 7 is in the tens digit, so that's 10 to the first power. The 4 is in the ones digit, that's 10 to the 0 power. So that's the base 10 number system. Log with nothing written there is understood to be a base 10. Okay, so base 10 is the number system we live in. There's base 6, which is hexadecimal, which is also, it's used in encryption. So if you're into computer science and password protection and stuff like that, encryption, hexadecimal is used a lot in that. So there's uses for this stuff. It's just not everybody uses it. You may use it, but you may not know the math behind it. Your passwords and all that stuff that's going on there. When your iPhone suggests a password for you, and it's that funky, weird, all kinds of random numbers and letters, a lot of that has been calculated through like hexadecimal stuff, so that it's you can't really undo it. It's very difficult to undo it. An encryption key is very hard to undo because it changes the base of all of the letters. When you type something on the computer, it's really written in binary, and the programming makes it in English where we can read it. But the encryption key takes the binary and changes it to a different base, and then you have to have the key to undo that. So it's a pretty cool thing out of that. But base 10 is when you don't have anything written there, that's base 10. Okay. The next common log is one that's more of a science related log, is the natural log, LN. This LN is the same thing as log with the letter E as the base. They will never write it log base E. They'll write LN. E is a number. It's kind of like pi. Pi, it's like 3.1459, a bunch of numbers after that. E is a number like that too. It's 2.71 and a bunch of decimals after that. I don't remember what it is now. But it's used a lot in the natural sciences. Why it's called natural log. Natural sciences. Exponential growth of bacteria, decay, like carbon dating and stuff like that. It's the E number comes up a lot in that. So that's where that's coming from. But to rewrite that as an exponential, that ln, the base is E. So it's E to the Y equals 6. Okay, so being able to rewrite an exponential from a logarithm. That's our first job in 4.3. Our second job in 4.3 is to go the other direction. So write the exponential as a logarithm. Letter on G. So here we have 5 to the negative 3 equals 1 over 125. So on this one, what's the base of our exponential? 5. So that becomes the base of the log. If you'll remember this, a logarithm is always equal to an exponent. So that means this log base 5 of something should be equal to what? Negative 3, because that's the exponent. So that leaves only one place for the 1 over 125. So that's rewritten from exponential form into logarithmic form. Put the comma in the wrong spot. Reading what I was doing. 10 to the 5th is equal to 100,000. So if I'm going to rewrite this in logarithmic form, that base is what? 10. But I don't need to write the 10. I can, but I don't have to. It's understood to be there. Most of the time when you look at, on the test or on the quizzes or on the final, they're not going to put the 10 there. It's not, mathematically, it's not wrong for it to be there because it is there, but they don't usually write it. Okay. 3 to the 4th equals 81. Let's rewrite that in logarithmic form. Log base what? Of equals, boom. Una más. Let's say we had e to the 5th equals y. So I don't know, remember what e is, what the number e is. So it's a base e. So what is the logarithm that's base e? ln, or we can say natural log, ln of y equals 5. Natural log of y equals 5. If you say ln, that's absolutely fine. I know who you're talking to, what they say. I typically say natural log, but ln is the same thing. Pretty easy thing there, right? So converting back and forth between the two. What good is that? Well, where it comes in handy is when we go to solve some equations. So that's the next thing in this lesson. So we're going to solve. Example K. Log base x of 16 equals 2. So we have a logarithmic equation. I don't really know how to solve logarithmic equations, but I did solve some exponential equations a little bit ago. So maybe I could rewrite it as an exponential and be able to solve it. So let's try that. How would I rewrite this as an exponential? X squared equals 16. Oh man, do I know how to solve that? How? Take the square root of both sides. On the number side, don't forget, because you brought the square root to the party, you got to put the plus or minus in there. Okay? So what is the square root of 16? 4. So it's plus or minus 4. Because technically, negative 4 squared is also 16, so it would work for that. So don't forget, if you put the square root in there, you got to do that plus or minus thing. Okay? So there was one of those cases where rewriting it as an exponential helped us solve it. Okay? Let's try. Let's try this one. Log base 4 of x equals 1/2. And I cannot explain to you why I write log in cursive and everything else in print. I don't know. I've always done it that way.
I see everyone do that though.
Do you? Okay.
Like a lot of, like on the calculator, it writes it in cursive.
What?
Yeah.
Does not.
Yes, it does.
No, it doesn't.
No, it doesn't.
No, it doesn't. Okay. It's like, now,
Maybe not.
I'm-
Maybe it's just because I've always had your wife do it.
yeah, and she does. She writes a
too.
lot in cursive. She writes a lot more stuff in cursive. I write what I call pursive. It's like print and cursive mixed together. Really ain't either. But I've always written log in cursive. I guess it's because my math teacher in high school wrote it in cursive. And I just picked it up from her, probably. That's what I guess. All right, what do we got? What do we do?
4 to the 1/2 equals
Oh, 4 to the 1/2. That's a fraction exponent. We had some of that not long ago. What is 4 to the 1/2? 2. So it's, and on this one, I don't do the plus or minus because I didn't bring the 1/2 power to the game. Remember, 1/2 power is the same thing as a square root. I didn't bring it in there. It was already there. So that's why I don't have the plus or minus on that. So it's just going to be 2. Okay, LM. Log base 36 of the square root of 6 equals x. Weird here. Okay, 36 to x equals the square root of 6. Okay, so this is kind of taking us back to section 4.2 where we've got numbers here on both sides and actually exponents. So this is where the knowing the fraction exponent stuff is important and being able to convert back and forth. So what I'm going to do is I'm going to write that as 6 to the 1/2. And then 36 is really 6 to what power? Not just x, but 36 is 6 squared. So now that looks a lot like what we did in 4.2, where we got the bases the same on each side. And then my equation would be 2x equals 1/2. How do I solve that? All right, if I divide a half by 2, what do I get? Take a half a candy bar and split it into 2 pieces. A fourth. Half of a half is a fourth. When you divide by 2, you're cutting something in half. So that's a fourth. It's a fun one. Log base 27 of 81 equals x. Okay, so we're starting out with this, and then 27 is 3 to the third. 81 is 3 to the fourth. Good. And my equation then becomes what? Yeah, 3x equals 4. Divide. Yeah, 4/3 is what x is. So here we got something taking what we had already learned and having to use it a little bit. Donut example. Log base 4 of x equals 5/2. This one's so simple it confuses us sometimes. What is this as an exponential? Yeah, 4 to the 5/2 equals x. Can we evaluate 4 to the 5/2? Yeah, it ends up being 32. So I just go to my calculator and I was like, 4 to the 5/2, that's got to be a number. 5 divided by 2, that's the 32. That's where that's coming from. That's not bad. One more. Log base square root of 7 of 49 equals x. All right, so that'd be 7 to the what on that side? I'll make that 49 over there. Not just x, but that's a square root of 7, right? To the x. Square root is 7 to what power? What's the exponent for the square root?
Okay.
No.
What?
That's the index. The exponent for a square root. 1/2. This is 7 to the 1/2 x equals, and you're right on the 49. Make it 7 squared. That's the right thing. But we want to make that 7 to a power on the left-hand side too. So the square root is a 1/2 power. A cubed root would be the 1/3 power. That sort of thing. Now we can drop those bases because we got them the same now. So we got 1/2 x is equal to 2. And then how do I solve that? Okay, so if I divide by a half, what's 2 divided by a half? No. 2 divided by a half. Think about $2 and you take 50, you divide that by 50 cents. How many 50 cents are in $2? 4 of them. It's too late. It's been a long day. And you lost an hour's sleep this weekend. So you got it. So if you're putting that into the calculator, this is usually where this happens. Some issues come up. If you're putting that into the calculator and you're dividing 2 divided by 1/2, put that 1/2 in parentheses. If you don't, it's come back as 1 because what it does is it divides 2 by 1 and gets 2, and then divides that by 2 and gets 1, which is incorrect. You got to put that in parentheses there. Okay, so that's logarithmic equations. Now, the last thing in this section is the log properties. Okay, so this is log properties. There are only 3 of them. Okay, you have the product property. And what is a product in math? Multiplication. So it's the answer to a multiplication problem. So if we have a logarithm, doesn't matter what base it is, these properties work no matter what the base is. And we're multiplying 2 things together on the inside. You can expand that and write it as 2 separate logs that are added together. You can also take an addition problem and condense it or make it into one single logarithm by changing addition into multiplication. So the product property, if you have things that are multiplied together inside of a log, they can spread out to be individuals that are added together. Opposite of a product would be a quotient. So we got a quotient property. So we have a logarithm, doesn't matter what base it is, but you have something divided inside of the logarithm. That turns into subtraction. Product property, addition, quotient property, subtraction. If you think about exponent rules, when you multiply like x squared times x to the third, you add the exponents together. When you divide like x to the fifth divided by x to the third, you subtract exponents. The properties of logarithms are the same as the properties of exponents. They do the same thing. Now, the last property is what's called the power property. And it says that log base a of x to the nth power. The power property says that exponent n comes down as a multiplier. That exponent drops down to the front. That's what happens. That's what's going to happen there. Okay. So we're going to do two things. The first thing is we're going to expand some logarithms. That means we're going to start with a single log and spread it out into a bunch of pieces. Then we're going to condense. The condensing is what you're going to do more of. The next week when we solve logarithmic equations, you'll have to condense to do those. That means write it as a single log. Because if you can rewrite it as a single log, you can get rid of that logarithm. But the expanding really helps us learn the rules, learn the properties. So we're going to start with expanding. So let's expand the log. I'm just going to abbreviate logs into a sum, not sum, S-O-M, S-U-M, / difference of logs. Know what letter we're on? Will be Q. All right. Here's our first one. Real easy one. Log base 7 of 8x. So what's going on inside of that logarithm? Multiplication between an 8 and an x. So we're going to split that up into log base 7 of 8 plus log base 7 of x. That easy. Okay. I'm just going to change the base there to log base 6 of 3xy. So on this one, how many pieces do I have? 3. Got 3 things that are being multiplied together in there, so that means I should have 3 terms in my expansion. I'm going to have a log base 6 of 3 plus a log base 6 of x plus a log base 6 of y. And we have expanded that logarithm. Okay. Using the product property. Okay. Log base 2 of 27 over x. What's going on between the 27 and the x? Division. So that's going to be subtraction. So log base 2, the numerator goes first, then the denominator is what's subtracted. Anything that's on the denominator will have a minus sign in front of it. That'll help us when we go to do the condensing. We remember that. Stuff from the denominator should be negative in the expanded form. Okay. Let's put those together. Log base 10 of 15x over 11. So this one has a little bit of multiplication in it, a little bit of division in it. So you can do this in 2 steps. I think after you've done them a few times, you'll start doing it in 1 step just out of natural ability, just because you get used to it, okay? The first thing that I would do is the big blaring thing here is this big fraction, so it's division. So I'm going to rewrite it as log of 15x minus log of 11. That's going to be my starting spot, okay? Now I look to see, can I break that up? And this guy has got a multiplication together. So I want to break that apart to be log of 15 plus log of x minus log of 11.
And if we put the base 10, it doesn't matter.
Yeah, it doesn't matter. If you wrote the 10 down there in the base, you don't have to, but you can if you want. Helps you. Okay. So that one kind of mixed together the multiplication and division properties. Log base 3 of x to the 7th. So here in this one, new thing, it's got an exponent in it this time. This is a power property. So that 7 is just going to drop down to the front. And we're going to have 7 times the log base 3 of x. And I wrote the little multiplication dot in there. You don't have to put that there. If you just wrote 7 log 3x, that's fine. But I just put that dot in there just so I know it's multiplication. Okay, that's not too bad. All right. This is where we really find out if we knew what we learned before. Out of water, we got to get finished soon. So, I see a radical. Anytime I see a radical in logarithms, you want to think about that as being an exponent. Okay? So what is the exponent on the x inside of this logarithm? Right now it's a 2, but it's underneath the cubed root. So it becomes 2 2/3. Yeah. The index of the radical becomes the denominator of the fraction exponent. Okay? The 2 on the x is the numerator of the exponent. The 3, that's the index of the radical, that becomes the denominator. Now that's a power property. So that 2/3 is just going to drop to the front. So there we had a power property mixed in there with the with that radical stuff happening. About to run out of letters. We got just a little bit more to go, but that's okay. We'll go home eventually. All right, so let's put together a little bit of the radical stuff with a little bit of multiplication stuff with the power rule or power property. So we've got an x squared times the 4th root of y cubed. So the first thing that I do on these, I don't even try to break them apart until I've fixed the radicals. I'm going to rewrite that radical as an exponent. So that, not x to the 3/4, but y to the 3/4. So log base 4 of x squared times y to the 3/4. That's the first thing that I do. Whether you think that step or you rewrite that step, it doesn't matter. That's the first thing that you want to do. Then, okay, how does this break apart? Addition, subtraction. It's multiplying, so they become what? Addition. So this is really going to be log base 4 of x squared plus log base 4 of y to the 3/4. Now, I'm doing one step at a time, but do you see where you could have done the power rule there at the same time? Most of you are going to, as you've done a few of these, you're going to start doing that all in one step instead of having to do 2 or 3 different steps. If you do 2 or 3 steps, It's like 10 seconds of your life. It doesn't really affect anything. But the more you do these, the more you will start doing more than one step at a time. So that 2 is going to drop to the front. That 3/4 is going to drop to the front of that one. 2 log base 4 of x plus 3/4 log base 4 of y. And you've split it up as much as you can. Let's do one more expansion, then we will condense. Wx comes out. Right? Natural log. Big fraction here, x y squared over w cubed square root of z. Man, that's a lot of stuff. This is a fun one. I know, my life must be really boring if this is fun. It is. I promise. I like it that way. All right. A lot of stuff going on here. What's the big thing that we see that start with the division? Break it apart first. Okay. Whether you do it in your head or you write it down. I'm going to write it down because it's notes. Either way, division, that's going to break apart into natural log of x, y squared, and then natural log of w cubed square root of z. It's a minus sign in between because it's division. Does that make sense so far? We are not done, but we're closer than we were. Now, before I can do power rule, I got to undo multiplication first. So this guy, what's it going to split up to be? Okay. Can I do the power rule on the y squared at the same time?
Yes.
Is that stepping too much? If I made that 2 natural log of y? Do we see that happening there? If you don't, just think, okay, this came from natural log of y squared. That 2 come down the front. That's where that was coming from. Okay. Notice that both of those pieces are positive. Right? Because that came from the numerator of the fraction. So this is a positive natural log of x. This is a positive 2 natural log of y. Now, let's go to split that apart. I got that radical in there, though. So what is the square root of z the same thing as? Z to the 1/2. Okay, that's important to have because if you don't have that fraction exponent, then you can't use the power rule on it. Got to have that fraction exponent for that. So because those came from the denominator, they're all going to have this minus sign in the front. So how's that going to split apart? It's going to be negative natural log of w cubed minus natural log of z to the 1/2. I could have done my power rule at the same time. They're both minuses because they both came from the denominator of the fraction. That's why they're both minuses. I'm going to do my power rule now. 3 drops down to the front, 1/2 drops down to the front. So my final answer, I've got natural log of x plus 2 natural log of y minus 3 natural log of w minus 1/2 natural log of z. And we've expanded that as far as it goes.
Why is it subtraction 1/2 natural log of z?
Because where is the square root of z from? It's from the denominator. anything from the denominator is going to have a minus sign on it. That will always be the case, and that may be something that we can write down. Denominator parts should be negative. So that being the case over here, those were denominator parts, so they have to have the minus sign in front of it. Numerator parts should be positive. Denominator parts should be negative. Good? All right, let's condense a little bit. Condensing, we already know the properties now. We've been doing them to do the expanding. So the condensing should go a little quicker because we've been working with those properties and we know them real well now. So condense to a single log. Yay. All right, log base 4 of x minus log base 4 of y. Real simple one to start with. So we're going backwards. So subtraction turns into division. So that's going to be log base 4 x over y. How do we know the y goes in the bottom? Not because it's the second one, but because it's negative. That's the reason. Because they may write it in a different order. So just because it's second or first doesn't matter. If it's positive, it goes to the numerator. If it's negative, it goes to the denominator. They'll try to trick you by writing it in a different order sometimes. Hey, we use the whole alphabet, kiddos. Yay! What do we do next? All right, so let's do this one. 3 log of x. I'm just using log base 10 here. Minus log of w plus 4 log y. This is one of those where they write it in a different order to try to screw with you a little bit, just to see if they can mess you up. Okay. So on this one, I got some power rule happening. I got some product rule happening, and I've got some quotient rule happening. I got them all. This is fun, right? Tell me what part goes. Go ahead, Callie. All right, so only one logarithm. You got the right parts in the top, but only one logarithm. So we're going to rewrite it as log. We got x to the third, and you're right, times. And then we're going to do the y to the fourth. That's on the top too. Why do we know both of those are on the top? Because they're positive. On the bottom, that's where the w is going to go because it's negative. And that's all you can do on that one. You condensed it into a single log. That's how you know you're done. You got only one single log. So when we condense those, there's only one log when you put them together. You don't have a log x, log y, log w. It's just that single log there in the stuff inside of there. Okay? We'll do double letters now. Just a couple more. I want to make sure we get some of the fraction exponent stuff in here too. So let's say we had 1/3 natural log of x plus 2/3 natural log of y minus natural log of w minus 6 natural log of z. This one's got a lot going on. It's got some fractions, it's got some addition, it's got some subtraction, got Got some regular exponents too that are not fraction exponents. So what do you want to undo first? My thinking is power rules. Undo those first before I start squishing it all together. X to the 1/3, natural log, y to the 2/3, natural log of w, natural log of z to the 6th. Okay.
So, natural
Okay.
log, parentheses, x to the 1/3 times y to the 2/3 divided by w z to the 6th.
That is absolutely correct. Can someone give me another version of that that doesn't have fraction exponents in it? Because this is right with fraction exponents, but they may not write it with fraction exponents. This is correct with that. So what root am I going to do here?
Would it be the cube root
Okay,
for x and
I want one cubed root on top,
okay.
one single cubed root. X and then y to the 2nd. Very good, Callie. And then on the bottom, it's still the w z to the 6th. They didn't change. Those are saying the same things. Both mathematically correct. But understand, when you get this, if that's not an answer choice on the final or on the quiz, know about the roots, changing it back to radicals. They may do that. They don't always do that. Sometimes they do, sometimes they don't. Mathematically, it's exactly the same, though. Okay? All right, last thing, punching it in the calculator. You got to know how to evaluate a logarithm with the calculator. So I'm going to show you that real quick. Easy thing. Evaluate with a calculator. Round to the nearest, let's see, 10 thousandths. How much is 10? How many places is 10 thousandths? So 10 thousandths, that would be, here's tenths, hundredths, thousandths, 10 thousandths. So that's 4 places. Okay, so what is this, AB? Yeah. AB, let's just say we had a regular log of 49. On the calculator, if it is just plain log, you've got a button for that. It's right over here beside the 7. That's the log base 10 button. Right beside the 4 is the LN, the natural log button. Okay? So we're going to use the log button. Log, and then 49. Hit enter. Go in 4 decimal places. So I look at the 9 that's after the 1. That's 5 or bigger, so it's going up. So 1.6902 is what it rounds to be. So approximately 1.6092. Where we have to learn a little bit here is log base 2 of 15. So we got a different base. The pen battery is low. Yeah, I know. Let's try another one. One of these that don't work. All right. So the calculator has a nice log base tool on that. Okay. To get there, you can hit alpha and window. So green button and then window, second one from the left there. Alpha, window, and the fifth option should be log base. Hit enter, and it puts little boxes there. So you just got to fill in the boxes. 2, 15. Go 4 decimal places, so it'd be 3.9069. Okay. AD. Let's do a natural log of 6. So we practice the natural log button. Yeah, natural log 6. Natural log's right there beside the 4. Hit that button. You don't have to close the parentheses even. So 1.7918. Very easy thing. And then AE, natural log, not natural log. Back up, sorry. Log base 1/2 of 71. What is that approximately? So how do we get the log? How do we put in a log base 1/2? Alpha window, option 5. Put in the 1/2. You can just do 1 divided by 2. You don't have to do the fraction button there. And then 71 goes in the other box. Crank it out. Hit enter. Negative 6.1497. Okay. Back when in the 1900s, we used to have to use this thing called the change of base formula. And it would allow you, if you were doing the log base 2 of 15, you could do that by doing the log of 15 divided by the log of 2. And it equals the same thing. You don't have to know change of base anymore because you guys have this nicer graphing calculator that does the log base thing. That's how, if you're stuck without a graphing calculator handy, if you've got a regular log button on the calculator, if you've got a scientific, you can do log base 2 of 15 by doing log base 10 of 15 divided by log base 10 of 2 and get you the same answer, okay? So that's sections 1, 2, and 3 of chapter 4. That's what this week is about, and it is that is all of it, believe it or not. So I'll write up the practice problems. You're welcome to look at those if you want to. I don't know how many people do that. It's a good thing to do, but not many people are doing it. So 4.2 was 1 through 99 odds, and 4.1. What did I do with that one? I had it. Threw it down somewhere. There's not that. Y'all have a great week. If you need anything, holler at me. I'll send out a post with all the stuff like I always do. Abby, buy your new phone. You dropped your something.